Okay, we're going to start our next section of chapter 20, which we're going to talk next about reflection of sound. Okay, so obviously we've dealt with the reflection of sound before. We call that an echo, right? And so we're going to talk about that. But the thing we have to keep in mind is that when sound encounters a wall or a tree or whatever, some of the sound is transmitted into the substance and some of the sound is reflected. And depending on the type of, on the substance of the material, will determine how much of that is reflected back, right? If a surface is smooth, the smoother the surface is, the more sound is reflected, okay? But if it's soft, if it's irregular, then a lot of that sound energy is absorbed, right, or transmitted into that substance, okay? And when we talk about sound, hitting a wall or something, um, it's just like if it's as if it was a light wave, right? It's just geometry. So the angle coming in has to equal the angle coming out, right? Those two angles have to be the same, okay? Um, However, when we start getting bouncing off of a lot of different walls, then we can get some of that wave interference that we talked about earlier. So if this is the wave coming in and it's reflecting out here, but then we have another wall here and another wall here, then when it hits this wall and bounces off and hits there and bounces off, and we continue to have other lines coming in and reflecting off, right? All right, we're going to get the opportunity for a lot of interference, wave interference. And now, depending on how those line up, if those are in phase or out of phase, we might get some destructive interference. We might get some constructive interference, right? And so if it undergoes multiple reflections and the sound wave, let me say it a different way, the reflected waves continue over here and over here. If those waves continue after these waves have ended, then we have what we call reverberations, okay? Now, if there is no reflection, then we're not going to obviously have reverberation, right? But when you get reflections, you get a lot more volume because there's the opportunity for constructive interference. When things get absorbed, let's look at what happens when things get absorbed, right? If that sound coming in just hits and dies right there, it's being absorbed into the substance and there's no reflection, you're going to get an area or room that might be sound dull and lifeless. So reflection is a good thing to a certain point. We've all probably been in rooms where it reflects too much and you can't really tell what the heck is going on sometimes. Okay. Um, Concert halls, auditoriums and gyms are a good place where we could talk about the balance of those two, because in those things, in a concert hall, for example, they put tiles or big uh, pieces of material on the ceilings and walls to absorb some of the sound, right? Because you have so many different sounds going on that if they were to echo and bounce off and reverberate, you might get a lot of distortion. And so they have to try to balance that, absorb some of the sound, but then leave some of the sound to reflect, okay? And so the study of the sound, of how much to reflect, how much to absorb, is called acoustics, right? That's a term that we probably are familiar with, right? So acoustics is the study of the bouncing and absorption of sound, all right? Um, they put things that are very reflective behind a stage where a concert might be happening, and they might put large reflected things above the stage, like in the ceiling, but they might put things that absorb it on the walls, okay? Um, so not anything that we're necessarily going to be tested on, but something kind of cool to think about. Gyms are notoriously um, loud because there's so much sound being reflected, because we don't typically spend the money to put things on the walls that absorb sound. Now, that's kind of cool because when it's loud and you're the home team, that reverberation is kind of fun. Makes it get a little crazy in there. But if you're a coach trying to coach and nobody can hear you, it's a little frustrating, but but that's just kind of the way it goes. So, but reflection, the other thing just to keep in mind is that the angle of incidence has to equal the angle of reflection. Okay. Now, when sound is absorbed into a material, we get a refraction of sound. Okay. When they go through a material, they actually bend. Okay. Because I don't know if you can think about this, but if you want to think about that for a second, it might be a good time to pause the video and think about why would something, when it goes into another medium, why would it bend? Well, and the answer is because what we talked about on Monday is that sound travels at different speeds in different materials, right? And so if you have air, right, versus, I don't know, we'll just say water, right? When the sound wave, let's go with that. When the sound wave hits, right, it's going to change speeds. And it's kind of like if you've ever, I don't know if you've ever done this before, but, and we'll talk about it more with light, but have you ever like had a two-wheel, something that's on two wheels and you're rolling it and and part like on a sidewalk and you're angling it towards some grass, right? So let me kind of draw that picture here for you. So here's a sidewalk and you're on the sidewalk and this is grass over here, right? And you got your two wheels. Let's go with some blue wheels, right? And this is one wheel and this is another wheel. And you're going in this direction, right? Well, what happens when this first wheel right here hits the grass, right? Well, it's going to slow down, but the wheel over here keeps going, okay? And so your wheels are going to turn, right? This wheel that hit the grass first is going to slow down, and this wheel that was still going fast is going to speed up, and it's going to actually cause your cart or whatever you're pushing to turn. Well, that's kind of what happens with refraction. Okay, as the light hits here, the angle that it's coming in is going to change when it hits water because it's going to speed up, right? And so it might go in this direction. Okay, so when sound enters a different medium, it's going to bend or refract because of the change in speeds in that medium. Okay, now this even happens in air when we talk about cold air and warm air. All right. On a warm day, for example, the air that's kind of closer to the ground is going to be warmer than the rest of the air. And what do we know about when the temperature increases? What do we know about the speed of sound in that air? Yep, that's right. It's going to speed up. Okay. And so if you have, let's say, here's the ground. Okay, and you have cool air here. Sorry, and warm air here. Sorry, I don't have my pen today, so I'm writing with my finger, and it's a little crazy. You have these two different airs. So let's say that you're a person right here. Okay, and you say something loud, right? And so your sound waves are going to kind of go like this, right? Well, what's going to happen is that when you have the cool air up on top and the warm air on the bottom, this part of your wave is going to be going faster. Faster than the part up above. And so it's actually going to bend the sound wave up a little bit, right? So if you're talking to your dog over here on the ground, right, you're going to have to, oh, sorry, that was very bad. You're going to have to talk a little louder or angle down a little bit more because that sound wave may bend up and miss your dog a little bit, right? If it's a long ways away. Okay. Now the opposite is also true. If this is the ground and here you are, okay, and you're going to talk again and send out waves, and we have warm air up above and cool air down below. Again, the part of the sound wave that's in the warmer air is going to go faster, right? And so what's going to happen is that upper part is going to go faster. It's going to bend that sound wave down. Okay. And this will become a little bit more important when we talk about light a little later on. Okay. But kind of a cool little thing to think about. And I'm sorry we don't think about it very much. But, if you think about when you're at a lake, right, you can hear things for a long ways away. Why? Because those sound waves are staying close to the ground where you are, right? Because a lake is going to be cooler air over a lake, right? It's water, especially at night. You can hear sounds from way far away across a lake, like they're right next to you, because that cooler air, it's bending those sound waves down, and they're kind of all congregating down here at water or ground level. Okay. So sound waves do not travel in straight line paths all the time. Okay. Now, obviously, sound also is different in water, as we talked about. Even in water, the different temperatures within the water can affect the speed of sound. Okay. So, like if they're trying to figure out how deep a certain part of the ocean is, well, they have to take into consideration that when they send a sound wave from the boat up on the top down to the bottom of the ocean floor, well, there's going to be a big temperature difference as that sound wave travels through the water. So they have to either calibrate and make exceptions for those differences if they know them, or they're going to know that their readings are going to be a little off. Okay. I think that's about it for water. Yeah, that's probably good. If you are talking about sound composed that has a higher frequency than what we can hear at 20,000 hertz, right? If we're talking about ultrasonic, um, we can use the reflecting and refracting of sound waves that are ultrasonic in order to come up with an image. Right? That's the whole thing behind an ultrasound machine, right? That they use to be able to see a baby inside a mother's womb, right? It's better than X-rays because you're not sending harmful X-rays into a woman. You're sending sound waves, right? They just happen to be too high for us to hear, right? But let's see, when you send a sound wave, an ultrasonic sound wave into the womb, right, there's parts of the womb that are going to absorb sound and parts of it that are going to reflect the sound, right? Bones and more dense material is going to reflect sound, where kind of the open space or the liquid filled space might absorb it more, right? So that's how they produce an image in an ultrasound machine, by using sound waves that are being reflected and refracted back into their machine. Okay, so that's kind of a cool thing. That's also obviously how things like dolphins and whales use sound. Bats use sound waves in order to locate different parts of their environment, based on ultrasonic transmissions. Okay. And I think that's all we're going to talk about for refraction of sound. Okay. So just kind of think about this for a second. An oceanic depth sounding vessel surveys the ocean bottom with ultrasonic sound that travels at an average of 1,530 meters per second. Isn't this pen so much better? In seawater, how deep is the water if the time delay of the echo from the ocean floor is 2 seconds? Right? So, meaning it's going down 1 second and coming back up 1 second. So, do you see how they can use sound waves, and they know the speed of it in water? Now, again, this is not going to be the speed the whole time, but they're going to say the average speed of speed of sound, in water, right? So how deep is the water? Well, if it takes 1 second to go down, right, because it takes 2 seconds total, if it takes 1 second to go down and 1 second to come back up, and the speed of sound in water is 1,530 meters per second, then the depth must be 1,530 meters. Okay. All right. The next thing we're going to talk about, and our last little thing we're going to talk about for today, is called forced vibrations. right? And I wish I wish we were in class so I could show you this, but if I'm holding on to a tuning fork, okay, and I hit it with a hammer, all right, it's not going to do much. You're going to hear a little ting, but then that's about it. But if I then was to hold that tuning fork on the top of a desk, right, and then hit it with the hammer, it'd be much louder. Why? Well, because the vibrations that that tuning fork is causing are going to be reflected in that table. And so I'm going to get more amplitude. I'm going to get more sound waves being produced than I would with just the tuning fork. Okay, and so this is what we call a forced vibration. I'm hitting the tuning fork, but by placing it on the table, I am forcing the table to vibrate at the same frequency that the tuning fork is. Okay, not only that, because of that reflecting surface, the tuning fork is actually going to vibrate longer than it would if it's in my hand, because some of those waves are going to bounce back into the tuning fork. They're at the same frequency, and so we're going to get some resonance, and it's going to cause those vibrations to continue longer. All right, so that's kind of a good thing to keep in mind when you're talking about sound. If you want something to be louder and last longer, you want to make sure there's a reflective surface that it is touching in order to force the vibrations. Okay, it's the same type of thing with a guitar or a music box or anything like that. Okay, all right. Here's the other crazy thing about this forced vibration and sound waves is that let's start with this. If I drop a baseball bat on a concrete floor and I drop a wrench on a concrete floor, I think it would be very obvious which is which, right? We can recognize those sounds. Why? Because they make a certain pitch, and their pitch is based on their material and how many vibrations per second that they naturally give off. Every substance has what we call a natural frequency. Okay, it I know it's obvious that a wrench and a baseball bat have a different natural frequency because they're made out of different things, right? Now, if you were to drop a ash bat versus a pine bat, then you might have a harder time distinguishing between their natural frequencies, but they would have natural frequencies nonetheless. Now, all atoms have a frequency. All different types of atoms have a frequency that they all naturally vibrate at. Okay, and that's something that's going to come into play when we talk a little bit more tomorrow about resonance, and when we even talk about light waves later on in future chapters. Okay, so everything in all things that are made of atoms have a natural frequency that their atoms want to vibrate at. Okay. All right, so that's going to do it for today. Tomorrow, we're going to talk a little bit more about resonance. I'm going to have a little video to show you, and then we're going to talk about interference and beats. So hopefully you enjoyed this a little bit better, and I will talk with you guys soon about questions on the homework.